Welcome and hello. This is a video tutorial in MODSIM, and in this lesson, we're going to be talking about irrigation return flow and pumping stream depletion. These are two similar topics that make sense to tackle in the same lesson. All right, what you see on the screen here is a network that I've already got sketched out. The reservoir flows to demand D1, and then we also have a non-storage node that connects to a sink. Let's go ahead and look at the properties for the reservoir first, and then we'll get into the irrigation return flow. All right, so our reservoir has a 1 million acre foot storage. That's its initial volume, a minimum volume of 0. Units are acre feet. Priority is 100. That's the only important information there. Apply OK. And then our demand node, let's look at the properties for that. Here on the general tab, we have a priority number. Let's set it to 90. So that's less than the reservoir. It has a higher priority. And then on the time series, let's go ahead and assign it a demand of 1,000 acre foot per month. That'll be for all months. And then on the groundwater tab, we're going to go ahead and add some infiltration data down here where it says groundwater infiltration. This is used in MODSIM to model the natural phenomenon where water delivered to a farm, for instance, will water the crops on the farm, but then a percentage of that water will infiltrate into the groundwater and then resurface at another location, such as this non-storage node NS1. So to do that, we will say demand D1. I'm going to create a table here. This is where I say which downstream location, a return location, that infiltrated water will arrive at. That's going to be NS1. It's our only choice because it's our only non-storage node in the network. The return fraction right here, I'm going to leave that at 1, so 100%, which is unrealistic, but let's just work with it for now. And then for the lag factor right here, this is where I say what percentage of that return flow occurs in the first time in the same time step, we'll say 80%, and the next time step we'll say 20%. So these lag values need to add up to 1. If I add another 2 here and try to click OK, it tells me it needs to sum to 1. I'm a little bit over. I'm going to retry the whole process of adding to 1, and boom, there we go. The infiltration fraction is also what I need to define right here. So if I say 0, then we're going to get no infiltration. But if I set it to, say, 0.1, which means 10% of the demand, which is 1,000 acre foot per month, we should see arriving at this NS1 based on the lags here, 80 and 20. All right, so this is a fairly simple model. Let's just go ahead and apply OK, save and run. And then we'll go ahead and check out the flow through NS1 to the sink, which will represent the amount of water infiltrated from demand D1, because there's no other inflow at this non-storage node NS1. All right, so let's go ahead and take a look at the reservoir first. This is the release of 1,000 acre foot per month. And then if I take a look at the volume, we see the volume of the reservoir is slowly decreasing, but there's still plenty of volume for additional releases. Okay. This flow right here is going to equal, changes the flow, boom. Here's our 1,000 acre foot per month that is served to our demand node, which is right here. Here's our 1,000 acre foot per month. Now, drum roll, please. Let's check out what sort of infiltration we have in this NS1 to sink link. And here it is. It's 80 for the first month, and then after that, it is 100, which represents the sum of the lags for the previous time periods times the multiplier of 0.1 times the 1,000 acre foot per month, which equalizes out to 100 acre feet per month. If I change the return fraction from 1 to 0.5, so let me go ahead and do that in my demand D1 properties here. I'm going to click on the groundwater tab, and then here's the fraction of 1. If I say edit and I change this to a 0.5, then basically the same numbers we saw before will just be half of what they were in this link from NS1 to the sink. So apply, okay. Let's run and save. Okay, I'm going to move this right down here a little bit more. How about something like that? Okay, let's check out what that link flow is. Right click and graph. And what we saw before is basically just scaled down to 50% what it was. Now it's 40 acre foot per month for the first month, and then 50 instead of 100 acre foot per month for the remainder of the year. So now that we've done a short example, I'm going to bring up the equation. This is the equation here. I'm on page 69 and 70 on the user's manual, irrigation return flow calculations. And here it is, equation 26. The irrigation return flow is the sum of the demand node values times the lag factors. The little delta here is the coefficient associated with the lag. Capital I represents the infiltration. Subscript little I is the demand node. Tau is the time lag, and then lowercase t is the time period. All right, so we're going to return to the model and just mix it up a little bit. I'm going to add a new consumptive demand. I'll call that D2. There we go. And then let's make a link from the reservoir serving D2. I'm going to add some data to D2. In the general tab, I'll also give that a priority of 90. And then in the time series tab, let's make this flow, how about 800 acre feet per month? So remember the demand here at D1 is 1,000 acre feet per month. And then in the groundwater tab, I'm going to create a table. And then what I'm going to do for my return location is NS1. So it's going to add more infiltration back to NS1. And so D1 and D2 will both be infiltrating to NS1. The fraction return, I'll leave that at 1. And then for the lags, I'll mix this up a little bit. I'll say 0.5 and then 0.35 and then 0.15. All right, so I'll click OK. Oops. Okay, retry. Hold on, I thought I had a 0.15 there. Okay. All right, there we go. And what I'm going to do for the infiltration fraction, it'll be 0.05. So from D1, it was zero point 0.1. Here it's 5% instead of 10%. Say, for instance, this NS1 node may be twice as close to demand D1. I don't know. Just making up some different numbers here to mix things up. We'll click Apply, click OK. Now let's run and save the model. The flow from NS1 to the sink is going to be larger than 40 in the first month and 50 after that. But how much more, I'm not really sure. So let's see. Go right click on the graph. All right. So we're up to 90, it looks like. The first month is 60. The second month is 84. And then after that, it's 90 acre feet per month through this link, simply based on the irrigation return flow from demand nodes D1 and D2. All right. The second part of this lesson, I want to talk about stream depletion due to groundwater pumping. And we do have an equation for that. Stream depletion from groundwater pumping. I'm on page 79 of the PDF file of the user's manual. The pumping stream depletion. This should look fairly similar. Instead of infiltration, now we have the groundwater pumping term. And instead of a little lowercase delta, we have a alpha, lowercase alpha, which represents, the groundwater and the response coefficients, they're called, with regard to the lag for each time period. The user manual also mentions further down, in MODSIM, groundwater pumping is assumed to provide only a supplemental water supply to satisfy demands where all available surface water supplies are fully exploited. So we're going to see how to do that as well. I'm going to create a new demand, which is right here. I'm going to call this one D3. This is going to be our pumping demand node. So I'll open up the properties for D3. I'm going to set the demand to 50 acre feet per month in the time series tab. The general tab, I'll set the priority to 90, just like the other two demand nodes. And then in the groundwater tab, I'm not going to touch the infiltration data down here, but what I will do is set the pumping data. So right now, I'm just going to say it's pumping its own 50 acre feet per month. Here are the units. And then the pumping priority, I'm going to set it to 5,001. So what that will do in the cost equation is set it to actually a cost of 10, a very small but positive cost. And that's how it ensures all natural flow links with small negative costs will have priority in satisfying the demand node instead of the groundwater pumping. But this priority cannot be so high that it actually is more expensive to pump the water than the cost associated with not satisfying a specific demand. The user manual also mentions that if you click this checkbox here, for networks with storage ownership rights, it guarantees that all surface water deliveries will be made before groundwater is pumped. All right, so let's go ahead and click the Create Table. Now what we're doing here is the depletion location. So with D1 and D2, we were adding water to non-storage node NS1 through infiltration. Now with pumping, I'm going to select NS1 as the non-storage node or the depletion location, which is going to lose water due to the pumping from node D3. All right, so this is cool. Let's make the fraction return 1. And then for the lags, let's do something different. How about 0.25, 0.5, and 0.25? So that refers to the same time step, the next time step, and then 2 time steps into the future. Okay, so click OK and apply. Okay, let's go ahead and run and save. All right, so that happened. I'm going to check on D3 first just to make sure it got its water. Yep, 50 acre foot per month. So it's pumping its own water. And now the link flow from NS1 to the sink, it used to be 90 acre feet per month after the first few months once it kind of hit equilibrium. Let's go ahead and see what effect this groundwater pumping depletion had on this link flow. So here's the graph. Okay, so now we're down to 40, which makes sense because it used to be 90 and now we're subtracting 50 because we set that fraction return to 1. If I set the fraction return to less than 1, then we'd have more flow through that link. So let's go back to the D3 properties. Then on the groundwater tab, and edit this table. Instead of a 1 here for the fraction return, but just call it 0.2. So 20% of 50 would be 10. So we should see 80. Let's go ahead and run it and then close. OK. And run the model. All right, so that ran. Let's check the link flow here. All right, so it's 80 instead of 90. Now this link flow could still be 80 and we could still be pumping more out of demand node D3 as long as we change that fraction. So right now we're only pumping 50 acre feet of water from D3. What if we increase it to 500 acre feet per water? But we still want to only deplete that 10 acre feet of water from this link or from NS1. To do that, we'll go ahead and modify a couple things in this demand node. So open up the properties. I'm going to go to the time series tab, change 50 to 500. I'm going to go to the groundwater tab, change 50 for the pumping rate back up to 500. Now instead of 0.2 as the fraction, I'm going to set this to 0.02. So just 2% of 500 is 10, just like 20% of 50 was 10. Apply. Okay, and then let's go ahead and one last time run this model. Let's confirm we have 500 acre feet per month pumped and delivered to that demand node. Yep. And then this link right here should look just like it did before. Yep. So the link flow is still 80 acre feet per month after the first few months. To summarize what we've done here in this lesson, it was about the infiltration return flow, like we demonstrated with demand nodes D1 and D2, and then the pumping stream depletion, which we saw using demand node D3.